Welcome to today's Tech Talk. Let me first introduce our keynote speaker. Dr. Asokan is a professor of computer science at the University of Waterloo, Canada, where he holds a David R. Cheriton Chair in Software Systems. He is also an adjunct professor at Aalto University, Finland. He received his doctorate in computer science from the University of Waterloo, Canada. Professor Asokan is primarily interested in understanding how to build systems that are simultaneously secure, easy to use, and inexpensive to deploy. He was born in Sri Lanka and did his early schooling in Matale, Jaffna, and Kandy before going overseas for tertiary education. He is a fellow of the Association for Computing Machinery, ACM, as well as of the Institute of Electrical and Electronics Engineers, IEEE. As per the Google Scholar records, Professor Asokan has published nearly 300 research articles, including around 50 US patents, and received 15,600 citations with an H index of 63. Professor Asokan was introduced to me by Professor Niranjan, who is attached to the School of Electronics and Computer Science, University of Southampton, UK. He was introduced in 2011. And with this introduction, the University of Jaffna invited Dr. Asokan as a keynote speaker for the first Jaffna International Research Conference that we refer as JUICE, held in July 2012. At that time, he was a distinguished researcher with a radio systems laboratory at Nokia Research Center, Helsinki, Finland. In today's Tech Talk, he will outline some security, privacy, and fairness challenges in AI systems, especially those based on machine learning. If time permits, he will discuss his work in exploring effective and defensive aspects of one such challenge, model extraction, in more detail. It is a very pleasure to have Professor Asokan with us today. So thank you for accepting our invitation beside your busy schedule and especially this bedtime. So it's over to you, Professor Asokan.
Thank you, Ramanan, and thank you for all the students who woke up early enough to show up at this time. The time difference between where I am and where you are makes this a little bit difficult. So it's like 10 p.m. Where I am now. So I appreciate that you showed up early in the morning. Like Dr. Ramanan said, I'm going to talk about confidence in AI systems. First part of it is going to be a high-level talk. I will not assume any background or expertise, so all of you should be able to follow along. And if there is time, I will go a little bit deeper into some of the research that my students have been doing. But I don't want to, in the 1 hour or so that we have, I really would like this to be interactive. So I encourage you to ask questions. I will monitor the chat, so feel free to stop me at any time and ask questions. If you like, you can also unmute yourself and ask in audio. And if you're comfortable asking in English, ask in English. Otherwise, you can ask in Tamil or Sinhala. Tamil ninga gota enak belangam. Sinhala nona ahanna mata therena naththam kawuru hari parivarthana karanna puluwan. So let's try to make it as interactive as possible and stop me at any time. Another sort of logistical details, so the slides that I'm going to show, they are already online on my webpage. So here is the link to my webpage. If you don't remember, you can Google for my last name. You will find my homepage, and there is a tab called Talks, and you will find this and other talks from recent times. Okay, so let me get started. So the premise of today's talk is something that I'm sure all of you are familiar with and have seen it firsthand. Artificial intelligence is growing by leaps and bounds. Especially in the last decade or so, it has become really popular in terms of not just research, but also investment in startups, investment in big companies and government funding and so on. So this is an example chart that shows the estimated market size in North America for AI-related businesses. And you can see that it's growing exponentially. And I could have picked any such chart. It doesn't need to be North America. It doesn't need to be in dollar amounts, but every prediction is that AI is going to grow dramatically, has been growing dramatically in the last few years, and it will continue to grow. But it's not just in terms of money or market size, but also in terms of breadth and scope, right? So AI, just like software has been in the last couple of decades, AI is going to influence all parts of our life. All professions are going to be affected by AI, and all aspects of life, whether it's your work, whether it's your leisure, whether your healthcare, everything is going to be affected by AI. So there have been efforts like precision medicine, where artificial intelligence systems can be used to diagnose and personalized, develop a personalized care regime for individuals. There are law enforcement has been using predictive software based on AI models for policing, so to predict where crimes would occur and try to make precautions. Human resources is using AI models to predict or help with hiring decision, to decide which candidate in an interview is likely to do well in the company. And of course, AI is also used for security and privacy as well, right? So intrusion detection systems, authentication systems, all of these are using AI. So we can take a step back and sort of think about how one would evaluate whether an AI-based system is good, right? So imagine that you are a CEO of a company and you want to buy a facial recognition-based authentication system. So you want people to log into your company systems, not using passwords, but using face recognition. And I come to you and say, I have a good face recognition systems. So how would you evaluate whether my system is good? What kinds of characteristics or features would you look for? Anybody want to try to give an answer? I'm trying to sort of make you interact a little bit so that this is not just me talking all the time, but get you involved as well. So this is not a trick question. I'm just asking, like, if it's a machine learning based or AI based system, can you think of what kind of characteristics would be used to evaluate whether it's a good system or not? So first of all, I think if it's a face recognition based system, you want the recognition to be accurate, right? So let's say that people want to be able to log in. So if Dr. Ramanan wants to log in, every time when he shows up and the camera senses his face, it should let him log in. It shouldn't say this is, it shouldn't decide that it's somebody else and refuse him to be him from logging in. So that's like saying that the rate of false negatives, so the correct person not being correctly identified, should be low. Similarly, if I try to log into Dr. Ramanan's account, the system should recognize that my face is not his face and therefore stop me from accessing. So that'll be a system having a low rate of false positives. So typically an AI-based system is evaluated in terms of whether the false positive rate is low and whether the false negative rate is low. And these are measures of accuracy. And obviously you want your system to be accurate. Another aspect might be performance. You want the system to do whatever recognition it does or whatever prediction it does in a reasonable amount of time. So if I'm logging in, I don't want the face recognition system to take 10 minutes to decide that my face is really me, right? So you want the inference speed to be fast enough. You want the resource consumption to be reasonable, right? So it shouldn't take a lot of memory and so on. So this is actually how traditionally AI-based or machine learning-based systems are evaluated. So when I talk about artificial intelligence, machine learning is sort of one type of artificial intelligence. I'm going to use the terms interchangeably because machine learning is the dominant form of artificial intelligence today, and much of the topics that I will touch on are particularly applicable to machine learning. So for the purpose of this talk, treat these two things as synonyms, even though machine learning is only one type of artificial intelligence. So is this enough to evaluate an AI-based system only by looking at how good, how effective it is, and how good its performance? And whenever somebody asks a rhetorical question like that, the answer is usually no, right? So it's I'm going to tell you that this is not enough. And the reason why this is not enough is the kinds of success that I talked about at the beginning, right? So when a technology becomes very successful, like AI is, it attracts a lot of attention. It attracts a lot of smart people who want to find, build clever systems using the technology. But it also attracts a lot of bad actors. And that's because there's a lot of money, there's a lot of business that's going to come from these technologies. And the bad actors try to find ways to circumvent or exploit problems in this technology for their own ends. And this could be because they want to make money out of this. This could be because they want to stop somebody else from benefiting, reduce the benefit that they can get legitimately by attacking their system. So there could be any kind of different types of motivations why bad actors want to interfere with a successful system. And we have seen this happening in previous technologies. So for example, internet, everybody will agree that internet has been a fundamentally revolutionary technology over the last sort of 30, 40 years. Initially, when internet was designed, the designers didn't consider this kind of adversarial behavior of bad actors who would come and exploit internet for their own benefits. So it was designed just like AI systems are being designed today. And the measures of evaluating whether a networking system is good did not consider this kind of bad actors. And we are paying the price for this now, right? So we see that all kinds of malicious activities like malware and breaking into systems and so on have become prominent on the internet because it's such a successful technology. And this is going to happen for AI as well. So I'm going to claim that the way to evaluate an AI-based system is not just effectiveness, not just performance, but whether it's trustworthy. And whether it's, by trustworthy, I mean that it should actually meet all these criteria, but in the presence of adversarial behavior, right? So going back to this example of face recognition system. So traditionally, a face recognition system would be evaluated by say, collecting data from maybe 100 or 1,000 users, so collecting photos of those users and showing that a system that's trained from this data would have low false negatives and low false positives. So in other words, whenever Dr. Ramanan wants to log in, he'll be allowed to log in. Whenever I try to log into his account, the system would recognize my face as being different from his face, and it'll stop me from logging in. But this is normal, non-adversarial behavior, right? If I'm really a bad actor and I want to break into Dr. Ramanan's account, I'm not going to use my face because I know that a good AI system is going to stop me. So I will do some kind of an adversarial behavior. Maybe I will wear glasses so that my face looks more similar to his face. Or maybe I will wear a mask. Or maybe I will put a wig so that instead of not having any hair, I look like having hair similar to him. So these are examples of adversarial behavior. And a good AI system should be able to remain effective and remain performant in the presence of such adversarial behavior. So what kind of behavior can an adversary bring? And then we are going to look at sort of security concerns and privacy concerns. So I'll do this by first sort of showing you an example of a particular kind of a problem. And then I'll take a step back and talk a little bit about how to systematically think about the landscape of hopefully all possible security and privacy problems in machine learning-based systems. So a common machine application of machine learning is image classification. So these are machine learning systems or machine learning models that learn to recognize classes of images, right? So for example, a popular data set for image classification systems consists of images of different types of objects. And the job of the classifier is, given a picture, it should say what kind of object is there in that picture. So if I give a picture like that, what would a good image classification system output? Anybody want to guess? Now, if I were lecturing in person, I'll point to one of you and ask a question. And now it's difficult for me to point to one of you. So I hope some of you are brave enough to help me out by trying to answer questions when I ask you. No? So maybe you are not familiar with this. So this is actually a school bus in North America. So in North America, in the US and Canada, kids don't go to school by public transport. Every school has a bunch of yellow buses like this, and they go around the neighborhood and pick up kids because usually the distances are too far and public transport is not very good. And so either parents drive their kids to school in their cars or they take the school bus. So a good classification system will recognize this as a school bus. But it turns out that if you add a little bit of noise to this image, a noise that sort of looks like this and scale down to have only a slight perturbation, the resulting picture, I'm sure you would all agree that it looks like the original picture. So if you, as a human, would classify this, you would still say it's a school bus, right? And it turns out that the state-of-the-art classification models, and this is from a paper about 6 years ago, would be completely misled by small amount of noise. So that would classify this, this picture as an ostrich. So what's going on here? That the small perturbations that will not fool a human will completely fool an image classification model. And you may think that, now what's the harm if a school bus is misclassified an ostrich, but image classification is going to be used in many sensitive settings as well, right? So imagine a autonomous self-driving car, right? So self-driving cars have the autonomous driving part has image classification models like this that would look at the input from the cameras, the front-facing cameras, and then try to understand, for example, traffic signs. So if an adversary could manipulate the traffic sign to add a little bit of noise so that humans can't recognize it, but an autonomous driving system will interpret a stop sign as a left turn sign or something like that, that can be catastrophic. So when this was discovered a few years ago, initially people were skeptical. They thought, well, I mean, this is a static picture and maybe there are small changes. This is not robust. This kind of misclassification is not robust to small changes. And quite soon people showed that now you could find perturbations like this. These are called small perturbations to form this kind of input that can fool the system even in more complex models. And such examples are called adversarial examples. Maybe I'll write it here. So adversarial examples are inputs that would that fool a machine learning system. See, can you? So what you see here is an example, is such an adversarial example. And people showed that you can find adversarial examples not only against simple pictures like this, but also in more complex systems. So here is another picture. Normally, a good system would classify this as a cat, but with some manipulation, the resulting adversarial example is classified. So in this case, it's classified as a monitor. And you will see that this evasion or this adversarial example is robust against all sorts of transformations. So even if the picture is twisted or focused or zoomed out or zoomed in, the machine learning model is consistently fooled into making the wrong decision. So I'm going to play this video, and you'll see that these are the classes that are recognized by the machine learning model. And for each class, it assigns a probability. And you will see that the desktop computer will typically get the highest probability, regardless of how the image is twisted or turned or zoomed in or zoomed out. Right? So you can see that quite quickly, the machine starts to conclude that this is a desktop computer, and it is robust against all kinds of transformations. So now he's like zooming it back, he's rotating it, and the model is still confused. So these adversarial examples are not just curiosities, but can be a real problem. And imagine that again, if this is a self-driving car, and regardless of what angle the picture is taken in, the self-driving car's model might still be fooled. Right? So this is a serious concern. And it's not just images. So here is an example with from a research paper from a few years ago, dealing with audio systems. So what you see here, what you see here is first they show how voice recognition is used in a smartphone like iPhone, where you say dial, and then you speak out a number, and the smartphone operating system will dial that number. So this is what you see first. Then they would sort of lock the phone and generate ultrasound command that humans can't hear, but the smartphone is fooled into thinking that it's a command to dial a number. So let's see this again. See if this works. So I seem to have a problem here, but like I said, I think the slides are in the on my webpage, so you can later download it and try to play this this audio. So essentially, what you see is that even in the presence of ultrasound, the smartphone is going to be fooled into thinking that a human is dialing a number. Okay, so I hope I have sort of convinced you that researchers have shown how to fool a machine learning system, in this case classification system, by changing the input in some way. But now let's take a step back and think about how to systematically identify all such adversarial behavior in a machine learning based system. So for that, we have to have a model of what a machine learning based system looks like. So I'm going to sort of make a rough model like that. So typically you start with the data set. The data set is collected from a bunch of data owners, right? So if it's like a face recognition system, the data set is images of people's faces, and it's actually collected from individuals. So each person might take photos of their face and give that as input to the data set. And once the data set is collected, there is potentially a human expert, whom we shall call the analyst, will use some kind of machine learning training software to train a machine learning model from this data set as the training data. And in the process, they might also typically use external libraries. And this is very common. Google makes some machine learning libraries, Facebook makes some machine learning libraries, and people don't start coding machine learning system from scratch, they use these publicly available libraries. And so they use this to build a machine learning model. And the machine learning model is the one that's going to do the prediction or classification or whatever task that you are thinking about. So as an example, like I showed you some image classification system, those are examples of machine learning model. Or another one that you might be familiar with is machine translation. So if you use Google Translate, that's a machine learning model that is sitting somewhere on Google servers in their cloud infrastructure, and you interact with the model via some prediction API, right? So typically the model can be given to a client, or the model is made available via some kind of an interface, and there might be some access control, some firewall that controls access so that the client doesn't have direct access to the bits and bytes of the model, but has to interact with the model via some API, some interface, right? So I think for our purposes, we can consider this as representative architecture for any type of machine learning system. So now let you in on a secret. I myself am not a machine learning expert. My area of expertise is system security. And this means that I'm interested in understanding how to build systems and make them secure. And a big part of designing secure systems is really understanding this adversarial behavior, right? So how can people try to compromise a system or manipulate a system and try to sort of systematically identify all the different ways in which that can happen, and then try to build in defenses. So even though I'm not a machine learning expert, I'm interested in applying the same kind of system security methodology, primarily because, like I explained in the beginning, machine learning is going to take over all our lives. And therefore, understanding adversarial behavior in machine learning systems is important, not just as an interesting research project, but as a matter of even life and death. It would not be an exaggeration to say that. So the way I work with my students is, some of my students are experts in machine learning, and I sort of help them to think about machine learning systems, help them to think about machine learning systems from a system security perspective. And this is what I'm going to sort of give you a flavor of now. So I'm going to argue that the way to systematically identify all the security and privacy problem in a big system like this is to ask two questions. Who is the adversary, and what is the adversary's target? And I'm going to claim that if you can identify all the possible adversaries here and what their targets are, what is it that they want to compromise, you will be able to have a complete picture of all the security and privacy problems that can arise from here. And as you can see, who is the adversary will depend on the perspective, right? There are many different players here. There are data owners, there are trainers, there are prediction service providers, there are clients. So already we have like 4 different parties here. Who is the adversary will depend on the perspective of which party we are talking about. And one of the other parties might be the adversary from the perspective of any given party, right? So this is the thing that we have to sort of systematically look at. So in the beginning, we looked at adversarial examples. So these are cases where the adversary manipulates the input, and the adversary's target is to fool the machine learning model into making a wrong decision or outputting a wrong prediction. So if you want to ask these 2 questions, we would sort of put the adversary somewhere here. So it's not the client, but somebody outside the system who is, it may be the client, or it may be somebody separate from the client. The adversary is going to manipulate the input to the machine learning model. So that's what's shown in red here. And the goal of the adversary, the target of the adversary, is to affect the output, right? So basically compromise the input and affect the output, meaning that the integrity of the model is compromised. And I briefly mentioned that autonomous systems, driving systems, like self-driving cars would be an example of systems that are vulnerable to this kind of manipulation, right? So assume that there's a stop sign, and the adversary wants the machine learning model to conclude that this is not a stop sign, but it's something else, like some speed limit sign, so that an autonomous car would not stop at the stop sign. It'll drive past that at high speed and then maybe cause an accident or something like that. So the way the adversary would do that is to manipulate the input by adding this little bit of noise, like we saw before. And then people have demonstrated that this is possible. So they add a little bit of noise, and the machine learning model will conclude that this is a completely different traffic sign. So in general, these are ways of evading models. And like I said, the first paper that showed how this is possible against neural networks was about 6 or 7 years ago. But the idea of adversarial examples and evading models goes way back. So I think there were papers already almost 20 years ago that showed this kind of adversarial classification for simpler type of machine learning models like decision trees and random forests and so on. And if you think about it, this is nothing specific to machine learning models as such, right? This is also like, humans are vulnerable to evasion or adversarial examples like that. So what would, can anyone sort of tell me an example of humans being fooled by inputs like this, manipulated inputs like this? Have you come across optical illusions? Like optical illusions that show like two lines that are in fact the same size, but if you sort of add some small lines on top of that, one line appears shorter than the other line, right? So that's an optical illusion, and you can think of an optical illusion as an adversarial example against the machine learning model that's inside our heads, right? You might have also heard about deep fakes. Deep fakes are where somebody takes a video and or like somebody takes my face and then generate a video out of my face and from a recording of my voice and make it look like I'm saying something that I never said, right? So that's again an adversarial example against you, against your perception system. So adversarial examples are nothing specific to machine learning as such. It appears to be something fundamental to systems like machine learning models, including the human brain. And but then, adversarial example can have drastic effects, like in the case of self-driving cars or maybe other examples. For example, we talked about initially, I gave you the example of an authentication system based on face recognition, right? So if I can make my, suppose you have a face recognition system that lets people log in based on recognizing their faces, and I want to log into Dr. Ramanan's account, I can try to figure out an adversarial example against his image so that I take my image and make some small manipulations, and that'll fool the system into thinking that my face is really his face. And in fact, there was a recent paper that showed that by localizing these perturbations to an eyeglass, so they can sort of specially craft an eyeglass, pair of glasses with some marks on the glasses, and by putting that glass on, I'll be able to fool the system into thinking that it's somebody else. Right, so there can be both safety concerns and security concerns in using a system like this. If I'm using adversarial examples against a system like this. So that's one. So we can take the sort of same kind of approach and think about other adversaries and other targets. So here is a second example. So now the adversary is a malicious client. That's the one that's in red here. And the target of the adversary is not try to fool the system, but try to learn something about the data set and the people who contributed data to the data set. And you might wonder why this is a problem, right? But think about data sets that contain sensitive information. So maybe there's like a medical diagnosis data set that's used to build a precision medicine model, right? A model that can diagnose patients based on their symptoms. So the data set itself has to be taken from real patients with real illnesses. right? So if a malicious adversary, by somehow querying this model, can figure out that somebody who contributed data to this data set has a particular illness, that would be a violation of privacy, right? So that's what this client is interested in. The client, a malicious client, wants to learn information about a particular data set, or maybe particular data owner who contributed to this data set. And the client does this by querying the machine learning model, by asking the machine learning model questions, or submitting input and getting the output back, and then try to figure out, try to infer what kind of data may have been used. So again, there have been papers that showed that it's possible to infer membership, meaning that you could tell whether a particular person contributed data to a data set, or it's also possible to invert the model. Inverting a model means that you don't find out about a particular person who contributed to the data set, but you try to find out sort of average representation of different classes in a classifier system. So again, going back to this example of a face recognition system, each class is one person, right? So each user is one class, and you use many photos of that person to train the model. And model inversion means that you can get a sort of an average representation of the class. And if you take an average representation of all my photos, that's going to look like me. So again, by querying the model, a malicious client may be able to figure out what a person who contributed data to this machine learning model look like. So that's a case of a malicious client trying to target privacy of data owners. So let me give you a third example. Again, we are sticking with the malicious client, but this time the client is interested in the machine learning model itself. So imagine that sometimes the model is not given to the client, but only the client is only allowed to access the model via some API, right? So if you go to Google and want to use Google Translate, you don't have the Google Translate model. Google will not give you that, but they'll give you an API. You can either type in some sentence, or you can use an API, and you can get the translation of the input that you want to give to the system. So in this case, what the malicious client wants to do is to actually steal this model that may be behind some firewall or whatever, right? And it will, so essentially it's targeting, the target of the adversary is the confidentiality of the model itself, which the model owner wants to keep confidential because that's their business asset. They want to make a business out of that, or want to make money out of that. And it turns out that by sending repeated queries, it's possible for a malicious client to gather enough information to build a so-called surrogate model. And this is because every time you ask a machine learning model, give an input and get some results back, it's leaking a small amount of information. And if you ask enough questions, then you'll be able to build your own model that is, by some measure, as good as the machine learning model. So again, there have been examples, and the papers that are highlighted in blue are papers that are done by my students. So my students also showed that in a paper a couple of years ago that you can steal fairly complex models in a realistic setting. So you can imagine that this is a problem for people who are trying to make a business out of training a machine learning model, right? So in the beginning, I showed you that the machine learning marketplace is going to grow exponentially. So there's a lot of money to be made there. And the adversary wants to deprive a legitimate model owner from making a business by stealing their model. Okay, now we'll think about a different kind of adversary. So until now, we sort of looked at adversaries who are on the far side of this prediction API. Now let's think about from the point of view of the user of a system. And the adversary now is the prediction service provider itself, right? So again, think about something like Google Translate. So Google is the prediction service provider, and I'm the client. I'm giving some input to Google and getting some output back, right? So what kind of misbehavior can happen here? So normally you are going to give the input to this prediction service for a particular purpose. Say in Google Translate, you are giving input to Google because you want it to be translated. But if the provider is malicious, they can take this input and use it for other purposes. And so think about a case where you have a cloud-based antivirus, like a virus detection system, a malware detection system. So whenever you want to install an application on your smartphone, you want to check whether that's potentially malicious. And that can be done. One way to do that would be to have the machine learning model that will decide whether an application is malicious, but the machine learning model is behind a cloud service. So each smartphone, whenever it wants to install an application, it will extract some information about that application, send it to the model as input here, and the model will then decide whether it is potentially malicious or not. So the normal expected behavior is that the prediction service provider should use this input only to decide whether it is potentially malicious software or not. But if it's a malicious service provider itself, it can do other things. For example, it can keep track of which users have what applications. And you might think that this is harmless, right? So if my antivirus provider learns all the applications I have on my phone, what's the big harm? It turns out that the set of applications that I have on my phone and that you have on your individual phones tells a lot about who you are, right? So there are people who have shown, so this is like a paper from colleagues of mine in Finland. They showed that if you tell them what applications you have on your smartphone, they will be able to tell a lot about you. They can predict your gender. They can evaluate or estimate your wealth. They can tell what your interests are, what your hobbies are, what your political beliefs are, what your religious beliefs are. All of this can be correlated to the set of applications you have on your device. So if a malicious antivirus provider, instead of sort of understanding what applications you have and telling you whether that's malicious or not, if they collect this information, that's very valuable and can be misused, right? It's valuable because it's a profile of their customers, and they can use this profile to serve advertisements or customize their service. But they can also learn a lot about individual users, which the users didn't intend to tell the service provider. And if you have been watching news about how, say, social networks like Facebook and others use this kind of profile information, and then how malicious parties try to use this information to subvert elections in countries, right? So you've probably heard about what happened in the US in 2016 and what happened in the UK when the Brexit elections happened, how this kind of profiling of people were used to target different political messages based on their profiles. You can see that these can have this kind of revealing user profiles to malicious parties can have really drastic consequences. So this is another example of such a case where the adversary is now a prediction service provider, and if a client reveals input, the prediction service provider could misuse that information. So what can you do about that? Like, every time you use Google Translate, you are actually sending the input to Google, right? And typically, the messages that you are translating can reveal quite a lot of information about you. So what you would ideally like is a way for you to use Google Translate or use any other machine learning model in such a way that the cloud service provider who hosts the model doesn't learn what the input is, doesn't learn what the output is, but can still allow clients to use this, use their model, right? So again, the second paper here is something that another student of mine did that actually made this possible. So this is, we call it oblivious neural network predictions. And oblivious as a term refers to this kind of setup where there's a model owner who has the model, there's a client who has an input and output, and they jointly compute evaluate the input on that model without the server learning what the input output are, and the client learning what the model is. That's what we call an oblivious neural network prediction. And it is possible to do that using cryptographic techniques and using other mechanisms. Okay, so I want to sort of touch on a couple of things, and then I'll start to wind down. So continuing with this same approach, the malicious party now could be this entity that provides this machine learning libraries, right? So Google or Facebook provides the libraries. If some of these libraries are corrupt, they could set things up in such a way that the machine learning model that is built using that software would be, it'll do the job that the trainer wants it to, the analyst wants it to do, but it can also be, could have sort of backdoors where for specifically crafted queries, it might reveal information about the data set, right? So for example, there are some sensitive information about data owners, and the libraries could arrange it so that the machine learning model, while it's doing its job, but if a particular, carefully crafted query comes along, it reveals additional information that would otherwise not be available. So this is again an adversary who is sitting outside the system, who is producing this software, and his goal is to compromise the privacy of this data set. So again, there have been examples of this. So in each of these slides, I point to links to research papers that show examples of the particular kind of adversary that I talk about in that particular slide. And like I said, you can find these slides from my homepage. So if you're interested in any one of these, go look at the papers and you might learn more. So the last thing that I want to talk about is an adversary who is a data owner itself, right? So now, initially we talked about clients as adversaries, then we talked about prediction service providers as adversaries, then we talk about the library providers. Now we're going to talk about data owners themselves as adversaries, right? So imagine that, and many machine learning designers do this, right? So if you have a smartphone, your smartphone is collecting data all the time, like from your speech, from your movements and so on. And this data is being sent to Google or Samsung or whoever, where they used to build machine learning models. So a malicious data owner could try to manipulate the data that's sent from their smartphone to the machine learning model that's being trained. And their goal is then to affect the machine learning model itself, right? So you can think about sort of where this might be useful. Suppose this is a machine learning model that is meant to detect malware or detect spam, right? So in email spam detection, this is quite a common example, right? So spam detectors are trained from emails, and the emails are of course sent by whoever is sending the email. So if somebody is sending spam, they can craft their spam email in such a way that if you train a model using this spam email, it'll misclassify a spam mail as a good mail, right? So nowadays it's not that common because spam detectors have become quite good, but about like 10 years ago, it was quite common for spammers to have a spam email, and then in sort of gray font, they would copy text from newspapers and books and so on and include that in the mail itself. That's an example of this kind of a behavior where they tried to influence the machine learning model into making a wrong decision by corrupting the data that they provide to the data set. So this is called poisoning. You can poison the input and use that to change the way the machine learning model behaves. So by now, I hope you sort of appreciate that by systematically thinking about who the adversary is and what their target is, you can identify different kinds of machine learning security and privacy problems. And once you, as they say in any kind of science, identifying the problem goes a long way in finding a solution. Once you know what the problem is, then finding a solution is relatively easy. Finding the problem is hard. So let's take a step back and think about, are these the only thing that you should worry about? should you only worry about, if you want to have a trustworthy machine learning system, is your concern only about malicious adversarial behavior? And we just saw that you can systematically identify all kinds of different behaviors and hopefully build, develop solutions for them. So now in the last few minutes, I want to touch on non-malicious behavior that affect the trustworthiness of machine learning models. So let me give a few examples. You may have heard this in the news, I think a few months ago, about potential racial bias in image previews in Twitter. So somebody noticed that if they posted a tweet on Twitter containing two photos, the photo of one photo containing two faces. One is the former US President Barack Obama, and the other one is the Republican leader of the Senate, Mitch McConnell. So these two faces were on a photo, and he posted this on Twitter, and Twitter then chooses to have a image preview, not the whole photo, but like one part of the photo. And it turned out that the image preview always chose Mitch McConnell's face, regardless of what the configuration of the original photo was. So that suggests that Twitter wasn't being malicious here, but there's something is going on that somehow tend to exhibit this behavior that looks like potentially racial bias. It's always picking the face of a white person over a black person. There were other concerns like this. So people, like I told you before, people are using machine learning models for predictive policing, and researchers have seen that this predictive policing works on historical data, and historical data can be biased against certain racial groups. And that means that the models that are trained from this kind of biased data also exhibit the same kind of biases. And so there's a movement to sort of say that predictive policing, where they try to sort of predict who would, whether somebody who was arrested for a crime is likely to reoffend, whether this kind of predictions can be biased in the sense that they can systematically disadvantage one particular ethnic group over other groups. So what's going on here? And it turns out that this is, there's no malicious behavior here, but there can be biases in the data, there can be biases in how the models are trained, and that can have negative outcomes like this. And this set of concerns are sometimes called fairness in machine learning. So machine learning models should not only be accurate, not only be fast, not only resist adversarial behavior, but should also be fair in some sense. And then this is a hard problem, and then it's also an active research area. And some of the difficulty comes from trying to evaluate machine learning models and not accounting for this kind of fairness consideration. So after this Mitch McConnell, Barack Obama picture scandal showed up, somebody actually tried to see if this also happens for cartoons. So they posted pictures containing these two characters from the series, the cartoon series Simpsons. One is called Lenny and the other one is called Carl. But the Twitter preview always picked Lenny. So the actual pictures were like this. And regardless of how it was organized, the preview always picked this character over the other character. And you can see that there's a potential bias here. And Twitter immediately responded by saying that no, they did test for bias against racial bias and gender bias, but obviously they didn't catch all of these. And later, I think they made an announcement saying that they are improving this. But even today, you can go to this link and you can see that this is still true, right? You can see that the preview still prefers this person over this other person. And it's not clear whether it is really just a skin color issue or whether it is lighting, but there is a bias here that systematically picks one kind of photo over the other. So even though I spent a lot of time talking about adversarial behavior, I think a truly trustworthy system, if you want to be, if you want us as citizens in a society to trust AI systems, we should not only make them resistant against adversarial behavior, we should also address this kind of fairness concerns and ethical and legal concerns as well. So I think I'm out of time, and therefore I will not talk about this specific research topic that I was going to discuss if I had time. But if you go to my webpage, you can see the slides that I would have used. And if you are interested, you can look at them and ask me questions afterwards. So maybe I'll stop here, and I'm hoping that some of you will be brave enough to ask some questions now. So normally they say that one trick is, instead of saying, do you have any questions? You can say, ask me 2 questions. So I want to see if students from University of Jaffna can rise to the challenge of asking me 2 questions.
Good evening, Dr. Asokan.
Okay, yeah, go ahead. I can hear you.
Yeah, so the thing you mentioned in like early slides, that adding noise to the machine learning model can completely misguide the predictions. So what we can do to overcome this issue? I mean, I didn't see a really good way. I mean, I also face this issue in my research project. So actually, what can we do to avoid this kind of behavior?
So this is still a very much an active research area. People have tried different techniques. So one technique is called adversarial training, where you actually train a model with adversarial examples. And it turns out that such models are more robust to adversarial examples. I don't think you can remove this susceptibility to adversarial examples completely, for the reason that it seems to be something that's more fundamental than machine learning models, right? Like even humans are fooled by optical illusions. But there can be techniques that can be used to make machine learning models more robust than they are today. And adversarial training is one such technique. So this is a very active research area, and it's also kind of an arms race. So there have been papers that show how to increase robustness of a model against adversarial examples. And then like a year later, there'll be another paper that showed an improved adversarial example technique that can defeat that system. So the short answer is nobody has a definitive answer whether it's even possible to make models completely robust, but it's an active research area. Does that answer you?
Thank you very much, Professor, for your valuable time and accepting our invitation. On behalf of the IEEE student branch of the University of Jaffna, I invite Ms. Ajandi, who is the secretary of the branch, to deliver the vote of thanks.
Thank you, sir. Sir, am I audible?
Yes, I can hear you.
Yes. So on behalf of the IEEE student branch of the University of Jaffna, I take this time to thank our speaker, Professor Asokan, for providing us idea on trustworthiness in AI systems, and also providing us with an idea on building an ML model with the support of some research papers and real-world scenarios. I also deeply appreciate for sparing us with his invaluable time in his busy schedule. And we are very much looking forward to working with you in future events as well. I'm also thankful to our head of the department, Mr. Suthakar, and to our IEEE student branch counselor, Dr. A. Ramanan, for guiding us through to the end of another successful event. Finally, I can't thank enough to all our participants for joining us to hear out our speaker. Thank you, sir, for your valuable time.